Hello, everyone, and welcome to Talk Nerdy. Today is Monday, August 5th, 2024, and I'm the host of the show, Dr. Cara Santa Maria. And as always, before we dive into this week's episode, I want to thank those of you who make Talk Nerdy possible. Remember, this podcast is and will always be 100% free to download. And the way that we keep it going is by relying on the support of individuals just like you. If you'd like to pledge your support on a per episode basis, all you've got to do is visit patreon.com/talknerdy. This week's top patrons include Anu Bharavaj, Daniel Lang, David J.E. Smith, Mary Neva, Rika Maharaj, Brian Holden, David Compton, Gabrielle F. Jaramillo, Joe Wilkinson, Pasquale Gelati, and Ulrika Hagman. And thank you so much to the hundreds of others who continue to support the show and to make it possible to make a brand new episode for you every single week. So this week we've got a good one. Every week it's a good one. But we've got another good one for you. I had the opportunity to sit down with Dr. Robyn Arianrhod. She's a science writer, a mathematician, a historian of science, and a physicist as well. Her PhD is in general relativity. And she writes about culture, science, mathematics, and science history. She also researches general relativity and the history of science at Monash University's School of Mathematics. She's the author of several books, but she has a new one out for us to learn from and enjoy. It's called Vector, a surprising story of space, time, and mathematical transformation. So without any further ado, here she is, Dr. Robyn Arianrhod. Well, Robyn, thank you so much for joining me today.
Oh, my pleasure. Thank you, Cara. It's great to be here.
So we're going to be talking about your new book, Vector, a surprising story of space, time, and mathematical transformation. And I say your new book because you have written a few books previously. And before we even get into the book, I want to talk about you because you are a mathematician, but you also are a science writer, and you have quite a bit of expertise in the history of science and even in physics. So what did you study in school? Like, how did you get to this place where you have such varied interests and areas of expertise?
Well, it's interesting. I at school in the old days in Australia, you had to choose between the sciences and the humanities, and I found that a terrible choice because I've always loved literature and history and things like that. But in the end, I did choose science. But because I loved in particular the fact that math is a language that enables physicists in particular to uncover extraordinary mysteries of the universe. So I saw that balance, that interest in literature kind of was satisfied by that idea of maths as a language, and that's what I try to bring out in my writing as well. But then once I got into uni, I decided that this is back in the days when a lot of radical thinking, and I decided that science was only going to lead to, more problems. Little did I know what we've got today. But anyway, so I actually left science completely dropped out. Lived a countercultural life without technology, by the way, because I felt technology was damaging to the environment. I was very, much a fan of what Rachel Carson and people like that were writing.
Yeah. And so you were in your late teens, early 20s at this point?
Yeah. And so I tried to live in a small community without any technology at all. And that was incredibly difficult.
Yeah. How long did that last?
Well, with varying levels. Well, I suppose the really, really very little technology was possibly about a year, and then we decided that it was a bit isolated, and so we would rig up an old car battery radio and get some radio to get some outside contact. I mean, we had outside. We did have a vehicle. That was the one thing we allowed ourselves because we had to go. We weren't yet self-sufficient. But the getting of the radio was so transformative for me. I'd never really been a radio listener because I wasn't really much of a TV watcher either then. But I realised just how wonderful radio can be in reaching way out into the wilderness where we were living and to connect people. And then I decided that, I remembered some of my old physics lessons and I started to read a bit more about the James Clerk Maxwell, who is the guy that actually wrote out the equations of electromagnetism. And in the process, those equations, talking about maths as a language, those equations led him to conjecture the possibility that there were, that light was an electromagnetic wave, which no one knew at the time. They thought it was a wave, but they didn't know what it was. And B, that there might be other radiations, such as radio waves. And his equations then led people such as Hertz to go off and generate the first known radio waves. And so I started getting into that connection. And then the next thing we got was wind-up telephones to connect just the houses, the few cottages in the community. They didn't go out into the outside world, and this is long before mobile phones. And, of course, that was all about electromagnetism. That was real analog. Wind the handle, you're turning the magnet, you're generating an electromagnetic field. So I started to think, well, the science behind the technology and this wonderfully simple but powerful technology is really important. And so, yes, then I decided to try and get back into science.
Oh my gosh, I love that path so much because, very often when I interview academics on the show, I don't think there is a traditional path. I think that's kind of I don't know. It's a misnomer now to call somebody a traditional academic. Almost everybody I speak with, and I think especially women, they find themselves ebbing and flowing with different offerings of life and different interests, and eventually sort of find that, I don't know, that direction, that vector, as it will. And the wonderful thing about the story that you've just shared is how these objects, these experiences with these objects that were sort of representative of, I don't know, the avoidance of the terrors of technology, especially against, during this kind of zeitgeist, this political climate, were the very things that brought you back into academia.
Yeah. And it's interesting, isn't it? And the other thing I have to say is wonder. The being way out in nature, with dark skies and a sort of preternatural feel to the place. I also was drawn to the wonder of the universe, which have then, of course, also related to getting into how this marvelous language of mathematics can reveal to us some of the mysteries of this extraordinary universe.
I love that so much. And I think we don't stop and just breathe that in nearly enough. We don't sit and talk about the wonder and the awe of the natural world, of the universe, of the tools that we have either discovered or developed or refined over generations to make sense of the natural world. So often that's sort of the purview, I guess people will say, or it's the department of religion and philosophy, but I think it's absolutely the department of science and mathematics and these other academic pursuits.
Absolutely. Look, I really agree with you because I've been thinking lately, there's so much angst around environmental issues now. Why wouldn't there be climate change and so much else? That almost, and loss of species, and it's also depressing but we must, if we're going to save it, we have to love it
Mm-hmm.
and wonder about it. And there's so much nourishment we can still draw, even as we're doing our best and we're being overwhelmed by the problems. It is important to just stop and look and be involved, be part of nature, which is what First Nations people long did too, and the early peoples didn't separate themselves so much from nature. So yes, it's interesting, isn't it?
It is. I mean, it's funny because we think of somehow math. There's gonna be a difference in how we shorten that word throughout the podcast because, of course, you say maths, and we in the U.S. say math.
Used to math,
But
I tell you.
but that mathematics itself, I love the conceptualization of mathematics as a language, and I think it's so important, the very kind of description that you paint for us about mathematics, because very often it's easy for folks who maybe had bad experiences in school, or for whom they didn't have the sort of mentorship or the examples or the patience, that might have been necessary as they were learning about mathematics, to see it as a function of the natural universe. I think very often we see it as something separate, something superimposed, something that's sort of like the opposite of nature. Like math is numbers and it's hard and it's rough around the edges and it's not nature. But really, math is how nature is quantified.
Yeah, and in that quantification, which can sound cold and detached, and in some ways, it is, and sometimes it's been bad. What Rachel Carson tried to say was that if you just focus on one aspect of a problem, like killing insects, you don't focus on the whole chain. What are the birds going to eat and so on. And so the same thing when you try to quantify any aspect of nature, there's that danger of reductionism. But what I love and what I think I like to get across and encourage is the fact that if you can get that quantitative language, you can then enter into realms that are so fantastic, so fantastical, so awesome in the literal sense of the word. That it's something. It's a powerful language in a way that no other language can do. Fancy coming up with the Big Bang and the sheer improbability of the existence of each one of us. If you take the Big Bang origin story on face value, as seems to be the accepted scientific theory today, just even that, gives you great emotional and philosophical food for thought and actually comfort in a way.
Oh, I agree wholeheartedly. I'm curious, before we get into some of the specific topics in the book, I have to ask, and usually I hate these questions, like, as a woman mathematician, and that is not where I'm going with this. You are a scientist, you are a mathematician, you are a science writer, but I can't help but notice that you're a woman, as a woman myself, and I know my own experiences learning mathematics as a young person. I was very much the classic standard definition of stereotype threat, of having been fascinated by logic puzzles and having loved doing arithmetic when I was young. And then at a very kind of almost predictable age, starting to notice that, well, I'm not getting the answers as fast as I thought I might. And maybe I'm just not good at this. And maybe the boys over there are so confident because it's easier for them. And maybe I should keep my mouth shut. And I'm curious, did you have a lot of like what we think of as the sort of stereotyped experiences for why uh, the bias persists with young boys and young girls in math?
Oh, look, it was terrible when I was young. It, I know, and I internalized, as you obviously did too, that we mustn't be so good. We're not as confident, so it must be easier for them. And in fact, that's what my teachers actually said, that they actually said that I did really well, but my male rival, if you like, he did it easily and naturally, whereas I had to work at it. That was their assumption. They never asked or followed up. They just and that was the way they categorized me. Um, and it was terrible. And if you were a girl, well, you were a nerd, and therefore you were sexless by definition. And it really the lack of the sapping of confidence that girls have anyway. But especially if you wanted to do something that was, in those days, a mostly male pursuit. Well, it stayed with me, right? I have to say, most of my life, I think.
Yeah, I hear you. I mean, I would agree. And just the assumption by so many actors involved along the way that somehow that is essentialist, that is the
Mm.
nature of boys and girls or the nature of men and women. And not even a thought to the fact that, like, these things are deeply reinforced in us by how you treat us, by
Yeah.
how you behave around us.
And, it's interesting. When I was writing one of my earlier book, which was about Seduced by Logic, which was about Emily du Châtelet and Mary Somerville, who were two early pioneering mathematical women. And, they persisted against the odds. But Mary Somerville in particular was very self-taught and came from lower middle class background. She didn't have anybody smoothing the way for her. Um, and later in her life, she really wrote about how she'd been very successful, a little bit as an actual research scientist herself, but mostly as a excellent expository science writer, um, and textbook writer. But she still felt that, hampered by this secret feeling that just women weren't meant for the really creative stuff. And that was back in the 19th century. And, there's you and me talking about it, still persisting, and probably to some extent still today for young women.
Ugh, absolutely. And the reality that, young women, young people of color, just young individuals who come from sort of the non-majority or non-normative class, that the reality is they have to work 10 times harder to be viewed as equivalent. And
Mm.
it's such a shame
Yeah.
that there's an assumption of superiority among white men, especially in fields like physics and mathematics and computer science, that there's an assumption of essentialist superiority that actually breeds mediocre white men scientists, if I'm being honest. It makes amazing women scientists because we bust our asses, but it doesn't really help the field as a whole across many reasons. The very people that you'd think that it's serving, it's actually harming them as well.
True. Actually, there's a very interesting survey that was done. I think it was done at Monash. I certainly heard about it from there by the engineering department, and they found that, by broadening their ranks to women in particular, but to more broader than the usual white male that in engineering, it brought in whole different ways of operating, of relating, of researching together. Women had a more collaborative style, for example, and that it benefited the discipline. And that was terrific to see that. That must have been 15 years ago that I read that. So people were starting to really, seriously realize that, broadening the scope was going to help the field,
Mhm.
not
And
hinder.
have you seen a change over your career thinking about your, early on as a student and a trainee, and then as a young mathematician, and then, as you continued on and saw kind of the makeup of the classrooms or the attitudes or, who has tenure, who's in positions of power. Obviously, we have not achieved parity, but have you seen a change in throughout your career?
Definitely, there's been a change at at my university, for example, the main one I know about, in terms of offering more encouragement to women. Uh, there's a lot more women staff and women getting promoted. I also keep a track of the number of women and men doing PhDs in Australian universities in these areas, in maths in particular. And there is an improvement, but of course, as you say, it's not definitely still not parity by a long shot. But yeah, certainly there's an awareness that I am both. I'm really pleased to see it, but I also regret that it wasn't there for me.
Of course. Yeah, yeah, that it's sort of that ever-changing, trajectory, I guess we could say, that you were having to pave certain ways, but it's so that many women after you,
Yeah,
can continue
yeah.
continue to build.
So that's very encouraging that is changing. Then there's just a lot more realization that this is a necessary thing and that women can achieve just as well as men.
Absolutely. And, it was thinking about the subject matter, thinking about mathematics and I don't know, even looking at my show, Talk Nerdy. I've been on air now, I think this is my 10th year. I've got over 500 episodes. I can probably, oh, thanks. I can probably count on two hands, maybe three, maybe four. I actually should have gone back to look, but how many episodes were specifically dedicated to mathematics? Very often it would be, a Hannah Fry or a Stephen Strogatz, or like an individual who is a well-known mathematician who has recently written a book, or has, something kind of new and different or interesting to say. But generally speaking, and this is at least ostensibly, it started as a science show. It was harder for me to not just find, but then highlight um, mathematics stories than it was physics stories, for example, or biology stories, or chemistry stories, or psychology stories. And I think that math has a PR problem. Like, we don't, it's not written about very often in the media or spoken about very often.
Well, no, you're absolutely right, and in fact, I thought I was taking a bit of a risk with this with vector, because it's quite mathematical, um, and it stretches. I think the general reader, has to have some interest in maths, um, because the more popular way is to. In fact, one of the things that got me back into, talking about back in the old days, what got me back into mathematics was reading, devouring popular physics books, and noticing on the back covers saying, here's a great read, popular physics. That's physics without the maths. And I thought, well, how can you get to the wondrousness of the ideas if you don't have the language? I mean, yes, you can translate much of it into ordinary language, but there's an understanding that you can only see if you have some fluency in that language itself. That is the language that gives us those things that you can then write about in ordinary language. So I thought that was really interesting, and that's what I wanted to do. Um, Particularly in in this book, and perhaps in my earlier Einstein's Heroes, yes, to sort of show how maths is the language that underpins so much of what we take for granted.
Yeah, I mean, it's obviously so incredibly important, and especially as somebody who is also quite interested in the history of science. It's kind of the difference between this is what we know, a series of facts, and this is how we know it, an exploration of process. And, the facts are always changing. Like, that's just how science works. But the process, it may be improving, but the fundamentals are there. And if you can truly understand the process, you'll always be able to find the facts.
Yeah. No, that's interesting.
I would love for you to maybe share with us, because I have to admit, I, being that kind of that young woman who had that stereotyped experience, I did lean away from it, and I went more into the social sciences. I came back around to some of the harder sciences, and then back around to the social sciences. But I was scared of certain math classes. Like, I did not take calculus in college. I stuck with, I think my required courses were in algebra, geometry, some trigonometry. And then I mostly dedicated my time to statistics, because I was, doing research psychology, and statistics was very important for the work that I was doing. But calculus was always something that felt out of reach. And so I will be the audience today, because I want to learn so many things. So the book is obviously about vectors, but not just vectors. Vectors are a type of tensor? And so I would love to start with just a brief explanation so that we can dig deeper into what those words even refer to.
Well, vector in the simplest form, and I don't know whether you probably wouldn't have done that in algebra classes, but often when it's introduced in school, it's presented as an arrow. You represent it as an arrow because it represents a quantity at its simplest level that has both magnitude and direction. So the length of the arrow can represent the magnitude, and the direction points in the direction. So, for example, forces and velocities and positions are vectors, because you need to specify both the direction and the magnitude. And the idea, to me, the idea of having a single symbol that represented more than one thing was really quite extraordinary when you think about it, because it took ages for humans to evolve number systems that enabled us to work on quantity. But once we started being able to develop a symbol that was able to express more than one thing, then we led to a whole new way of looking at the world. So with the arrow, you can not only represent it as a geometrical arrow, which is a nice way to look at it, but you can also represent it as a list of components, and the components are what you get if you measure the arrow from the X, Y, and Z coordinates, which you would have done in algebra. If you draw a point on the plane and then draw an arrow to the origin, then that gives you your vector. And if you measure that line in each of the directions, they're the components. So the other way of writing a vector is to list its components, and in 3 dimensions there would be 3 of them. So you've got 3 bits of information there. And once you have a list, what's to say you can't go to 4 dimensions, as in space-time, or 10 or 11, as in string theory, and so on. It opens up a whole new way of thinking once you can represent more than one thing in the one symbol. And these lists, had special symbols to describe them, to denote them. But working, and what's interesting is that, maths in a way evolved from practical problems, and some of the earliest mathematical records that we know of, say the Mesopotamian clay tablets, and that have survived so well, and a lot of them contain lists of measurements, for example. But the thing that happened in the 19th century was that lists then became mathematical entities in themselves, and that with rules for how you could combine them, including calculus. So there's vector calculus, where you can take derivatives and integrate. And derivatives that just show you how they change in space or time. So that's very important, taking derivatives, say, of electromagnetic field vectors, tells you how they change in space and time, and you need to know that because electromagnetism works. Electric fields and magnetic fields generate each other if they're changing. So you need derivatives to represent that changing, those changing fields, those changing vectors.
It's all so fascinating. When I love this idea that you mentioned before of like, okay, I can represent this with an arrow, which has obviously it's on a 2-dimensional plane, but it has 3 dimensions of information, and we can visualize 3 dimensions because we live in a 3-dimensional world. And then you add this 4th dimension, which is time. And I think that we can, to some extent, visualize that. You know, if I say we want to go to dinner later tonight, like on TV, they always go like, dinner tonight? And they go, yeah. And then they walk away. And I'm like, how do they know when they're going to meet up? Like they never give you any of the details. In real life, you would say, we're going to meet at this address and it's on the 3rd floor and it's going to be at 7 p.m. And so now you have X, Y, Z, and you've got the time, the 4th dimension there. And that gives you that point in space, right? And that point can also be moving in space. But then you start to add a 5th and a 6th, and like you said, an 11th in string theory. And I've always asked scientists and mathematicians this. You can make sense of it numerically because those tables that you were talking about become fundamentally important there. Do you use any sort of visual representation? Is there a way that you analogize? That is a terrible use of that word. Okay, that's not the right word to use. But is there a way that you conceptualize more than 4 dimensions without just looking at the math?
Look, there might be, and I know I think I mentioned it briefly in Vector that back in the 19th century when there became a fascination with the 4th dimension that had a sort of mystical, perhaps there were ghosts or whatever dimension to it. And some mathematicians were looking at trying to imagine extraordinary 3-dimensional and build models of 3-dimensional surfaces that would have been hypersurfaces of an object in a bigger dimension. So you can do that sort of geometric thing is way beyond my ability to visualize, but people were doing that, and some people can do it. But what I love about algebra and the lists and the rules that go with combining the lists is that you don't need to turn your head inside out trying to visualize.
Right.
You just get familiar with the language. And, it's really interesting that the guy that first gave us the rules of vector maths, the Irishman William Rowan Hamilton, he was actually trying to solve a problem of algebraically representing rotations in 3-dimensional space. And that's an interesting question because in 2 dimensions, if you were to rotate an arrow, say, by 20 degrees and then do it by 30 degrees, so that all up you'd have it by 50 degrees, and then if you did it the other way, you went 30 degrees first and then 20 degrees, you still end up with a 50-degree rotation.
Right, yeah, it looks the same.
But in 3 dimensions, it doesn't.
Mm-hmm.
So, for example, if you had a book on a table and you had the front cover facing up and the spine was towards you, and then you rotated it clockwise through 90 degrees, so the spine was on your left. So that was a 2D rotation in the XY plane, and then you flipped it over clockwise until it was face down. So you're rotating in the vertical plane, so you've used up all 3 dimensions. Then you'll notice that the book's spine is on your right. But if you do it the other way, you turn it over first and then you rotate it clockwise towards you, the spine will end up on your left. And this really puzzled Hamilton because in ordinary, the 4,000 years of mathematical history that preceded it, you always said that 2 lots of 3 apples was the same as 3 lots of 2 apples.
Yeah.
But here, there was a difference. There was a different kind of multiplication. That is what we call non-commutative. It doesn't do it one way is not the same as doing it the other. And that was a huge problem for him. And, of course, now non-commutative algebras are so important. I mean, for example, Heisenberg's uncertainty principle is an example of the non-commutative law. General relativity, the curvature of space-time, is an example of where parallel lines, when you're moving along a curve on a curved surface, if you go one way to do a loop, your arrow in the end, your tangent arrows end up pointing in the opposite way. So if you go the other way, and that gives you a measure of the curvature. So this non-commutativity has actually ended up being extraordinarily fruitful, but it really puzzled Hamilton to start with. How can I introduce into math something that seems to break a time-honoured law of mathematics? So that was he was so excited when he discovered it that he happened to be having this final insight stroke of genius when he was out walking and he was passing by a bridge, and he took out his penknife and carved the formula into the bridge. So it's been celebrated pretty much ever since as a wonderful ecstatic act of minor vandalism.
I've long been curious about that experience because, I think in many different fields of inquiry, big discoveries, eureka moments can often be conceived by the peers in the field as either exciting moments of wow, the veil has been lifted. Holy crap, we can finally solve this problem that we've all been working on. And in other examples, we can point to plenty of times where it was pure heresy, where individuals were like, that's not possible. This is how it's always been done. You're going to realize that you're flawed somewhere along the way. I'm curious, does mathematics as a whole, like when you think back to the history of mathematics, follow similar trajectories? Like there are the highs and the lows, the wins and the people being shunned, and the people who are ahead of their time who never were given the credit that they deserved. You see all the same things there?
Absolutely, and Hamilton, I said that his graffiti's been celebrated ever since. Well, that's not quite true. It probably took half a century for people to
right.
what he'd done, and he was already very famous when he did that. But he was actually scorned by some of the leading lights because they thought his new system was useless. It didn't tell us any more than we already had. There was no need to have this system of notation and symbolism that allowed you to see the whole problem at once. And that goes back to what you were asking me about visual analogies. One of the ways of looking at how algebraic symbolism can help with that is in fact this vector hole notation. So, and by that I mean I was talking about the lists of components, but often they're written with a single symbol, so that vector it's usually often written as with boldface to distinguish it from an ordinary number. And then once you write the rules in those whole vector forms, you don't write out all the components, you get this beautifully elegant notation for expressing the laws of physics. And an example are Maxwell's equations of electromagnetism that I was talking about. And you can actually see there's a symbol, this is in the calculus part, there are two symbols for two kinds of vector multiplication. And one's a scalar product and one's a vector product. And one has the effect of a curl. And if you were to scatter, for example, iron filings on a disc around and thread through a wire and put a current through it, to see how the changing current was affecting the magnetic field surrounding it, you'd see that the iron filings all formed loops. They were curling around the wire. And so Maxwell actually created the term curl, which is a vector operation, a vector calculus operation that we use. So you'd see that simple symbol curl of the magnetic field equals whatever it, is related to the current flowing, for example. And so automatically the symbol tells you once you're used to that language, this is curling. There's a curl going on here. It tells you something. And the other symbol, it tells you how the vector arrows, if you like, are diverging away from the source. So the symbols themselves, once you learn to read them, encode a sort of visual, visual clues that make it make sense of the physics. In the early days, algebra was all written in words.
Oh, wow, really?
Yeah, it wasn't until the early 1600s that symbolism really took off.
Can you imagine the books?
I know.
Oh, my God.
I know. So you imagine trying to do a simple equation, like take the square of the unknown number and add 6 to it and multiply that by, the unknown number again, and then let that equal 25 and find out what the unknown number was, and you write it out in a simple equation, and visually you can see straight away. It opens the way to solutions. So I'm fascinated by that kind of evolution of symbolism, symbolic representation of quantitative relationships.
Oh, absolutely. I think about statistics in that way all the time, right? Statistics are these numerical and symbolic representations of large sets of data. It's just like there's all this information. How can I communicate the shape of this data? How can I communicate the direction of the data? How the data relates to itself through symbols and basically shorthand? How can I learn a lot about hundreds or thousands of numbers by this very simple notation?
Yeah, and often a beautiful equation, or certainly algebraic expression. So yes, it is extraordinary, isn't it? And that's a good example of taking all that information and representing it by something like even the average. The simple thing like the average or the median, let alone the standard deviation or things like that. And that tells you a lot about, in three symbols of, as you say, what could be hundreds of or more pieces of data.
How often do you think mathematics, especially at the kind of collegiate and the graduate levels, are taught and are explored in a metaphorical or a representative sense? I think we've sort of talked about how there are these operations and these representations of something, whether we're talking about a quantification of, 3 sets of 8 apples or 8 sets of 3 apples. When you're young and you're learning how to count and you're learning your simple mathematic operations, that's what it is. It's here's an apple and I take one away, and you visualize it that way. And then you continue to learn these more complex things like the curls you mentioned. And as you were saying that, I could see one of these maps of the planet, of planet Earth with all of the magnetic kind of, I don't know, fields like shooting out of it. And I could see the curls, like I could see a real visual representation. And then eventually that shorthand becomes so deeply understood. It becomes a language that is spoken. How often then do you go back and say, what does that look like to you? Let's envision this thing that we're describing in reality now. Let's retranslate it back to the very phenomenon that we're describing mathematically.
Well, in my experience, not nearly enough. Not nearly often enough. I think there's often especially teaching maths is difficult in the sense that it's sequential.
Mm-hmm.
And you have to.
Oh, right. It builds on itself. You have to know things to know new things.
Yeah. And so, lecturers and to some extent teachers are constrained by the syllabus that, you have to get this much done. And so there's a lot of those sorts of pressures that mitigate against a more thoroughgoing, slightly perhaps tangential exploration of the roots of numbers. Actually, I think there is a movement now in maths education to look at it in its historical context, rather than present ideas as facts engraved in stone, handed down from, on high. There's a move towards teaching how that evolved, which is sort of gets back to your question. If you don't look at where the symbols come from, you're not going to necessarily even be able to see the curl, for example. You just say, oh, that's curl, and you don't actually translate it in your head into a physical system. I mean, if you're a physicist working with that, or a maths researcher or somebody, you would. But in terms of most of our classes, I think it's too easy for kids to just want to know how to use it and get the right answer.
Right. It's almost like if somebody is learning a language, and instead of learning what are verbs and how they conjugate them and what are nouns and what's the difference and how do you modify verbs, if they just learn phrases and they know, well, this phrase generally means that and this phrase generally means that, you can get by with those phrases, but you can't really use them. You can make use of them, but you can't modify them, you can't adjust them, you can't adapt them to the past tense and the present tense, and that person over here versus this person over here. And so it can, but that's almost like how a lot of people learn mathematics, I think, is they never go back to those roots of what it is, why the hell they're even doing these operations and what they represent in the real world.
It's wonderful. I was doing some research for quite a while, but sort of COVID put stop to that with all the lockdowns and everything, but with a colleague. And I remember when we'd get stuck on a problem, he'd go, let's go back to the master. And he would go back and look at, on what Einstein wrote or what Maxwell wrote or whoever, was the relevant person. And because once you go back to the origins of things, you can see how the concept developed and what it was for. And it often gives you a much better understanding of what you're trying to do today. So I really try to bring that out because I think a lot of science reporting and writing today is really reporting on the latest development, the latest shiny new tech or the latest breakthrough or whatever, and that's all very important. But often people don't care anymore, or editors don't seem to care anymore about the origins of these concepts. And I think that's the mistake in trying to get an educated public to engage with and understand and get some real appreciation for the role of mathematics, for example, or science in general. Just like you would expect a person who's engaged with life to have some sort of appreciation for music and literature. And so I think that this emphasis on sort of breathless reporting of the latest, which may or may not end up being the final, but without so much emphasis on the concepts underlying it and certain origins of them. It goes back to what we were saying earlier about wonder too. It's all too overwhelming. I find a lot of stuff about science, it's too overwhelming.
Oh, 100%. And when it's completely detached from reality, or when it's completely like decontextualized, it can feel esoteric, right? And the minute something feels esoteric and it doesn't apply to me, it's very hard for me to remember anything I just heard.
Yeah.
I have to attach it to the things that already exist in my mind. It has to make sense within the heuristics that have already been laid down.
And to inspire your imagination. Not
Absolutely.
just give you, facts, exciting facts, exciting as they may be. But, so I think that's very important to look at those origins, like you were saying about looking at the origins of language as well, ordinary written and spoken language.
Yeah, I mean, it's so funny. I would never think before I sat down with you today that there would be a deep parallel between this very episode and the very last episode that I recorded with Daisy Dunn, who is a classicist. And we were talking about how she's reading these original texts, in ancient Greek and in these Latin languages and doing her own translations and interpretations, and how going back to, like, I remember taking a history and systems of psychology course, and I mentioned this on the last episode, so I won't talk about it for too long. But the way it was taught was so brilliant. It was, well, I'm going to read the words directly from Darwin, directly from Freud, directly from, Viktor Frankl, or from these different individuals who are influencing thought. And instead of reading some historian's interpretation of, I want to hear what they said.
Yeah.
Yeah, like, it's so rare to learn it that way. And every time I did, I was always like, wow, what a racist asshole. Like, it was always pretty amazing how often when you read the first, the first line of something, there's so much more depth and context to it. And there's so much more hints about the time and the era and the problems that individuals were facing, and the, the assumptions and the biases. And that all gets watered down when we read modern interpretations of those things.
Yeah, absolutely. I agree. And so it's fascinating about the parallels, isn't it? But it's,
right.
As I said, maths is a language. So, in that way, it's perhaps not so surprising, but we don't think about it. We don't think about making those connections enough.
I don't think we do. And I don't think that we take the time, like we said before, to contextualize. We start with context, and then we get deep into the sort of the lexical component of it, and then we stay there so often. And I think that if we came back to contextualizing both the history of how we know what we know, but also really what are these numbers and these notations representing? How can we now do things in the world with this information? What is this telling us about the universe that we live in? It's unfortunate that we don't revisit those questions as often in mathematics education, because I do think that more students would connect to the subject and not feel like it was some, I don't know, core requirement that they have to do and get over with.
Yeah, that's the problem, isn't it? Having to get over with it.
Right. And it doesn't help that parents and culture and television and society, all of the influence are math is hard, math is boring, math is, I don't remember this is confusing, you're never going to use this, which none of that is really true, but it's all been, I don't know, it's how it's talked about, isn't it?
Yeah. And, it's interesting because, a lot of kids do say that, well, why should I learn this? I'm never going to use it. And even if they don't, it saddens me that they don't actually find it fascinating, in the sense of reading a good book or listening to some music or whatever, that appreciation I was talking about before. So if you present it as a core thing that you have to do, and you, as you said, you decontextualize it, and you don't talk about the linguistic aspect of it and the wonder of it, then people are going to just worry about what use it is. And although use is very important, so is the beauty of maths. In fact, it was interesting, there was a survey done a little while ago among academics in Australia, and I think it was about people responding. There was a change to the national curriculum that was going to emphasize computation and more, and that's all important. And if you go back to those Mesopotamians, a lot of what they were doing was just computation. That's sort of what's helped birth things such as vectors. But it's a lot of the mathematicians wrote in and said, yes, but what about the beauty? We have to teach that as well, because not everybody will be using higher level maths, even in high school level maths specifically. But they need to be exposed to it, just like they need to be exposed to good books, and then they can choose what they want to do.
It's so true. I think about, I have to keep going back to statistics because that's my foundation. But when you start getting into more complex, multivariate, or honestly, even when you're looking at univariate statistics, it, doing a statistical analysis by hand, long form, it's a bear. And very often when you're in these courses, you learn how to do it, you do it once or twice, and then they go, okay, now the calculator's going to do it for you. The software program's going to do it, but you still needed to know how to do it. And I think of it that way, right? Like we have tools that help us calculate. It's important to learn how to do it. It's important to kind of prove to ourselves that we can. And in doing it, you learn all of the whys about it. But we do have calculators. Why are we spending so much time teaching children to calculate when they have tools to help them do that, when all of that time we could be spending teaching them why it's so fascinating that they can calculate?
Yes. Yeah. Yeah, it's tricky, isn't it? How do you get the right balance in a curriculum that, has a limited time available?
Right.
And as I said before, it has to build up certain skills. Like any language, you have to build on. You can't do French 2 without French 1. So
Right.
you need to have a certain level of the grammar under your belt. So yeah, look, I do find it tricky with that, which is partly why I write the books I write, because it gives me more scope than
Mm.
it would to do in a tight course.
So then I'm curious, sort of obviously there's so many things in the book we never got to, but as we're sort of wrapping up the hour, I'm curious, you mentioned all the way at the beginning of the conversation, seeing this rise in popular science and especially in popular physics, and like it was the bubblegum version of it's physics without the math. And you're like, wait, what? And so your approach is different. I mean, it doesn't kind of follow that I guess bubblegum approach to popular science writing. And so I'm curious, how do you hope your books to be read? How do you hope your books to be received, especially if the individual who picks up the book either has a chip on their shoulder about mathematics or they literally don't remember anything from the courses that they took? How are you hoping to, I don't know, communicate, influence, reach them?
Well, probably in my earlier books, I made sure I had a lot of history and biography as well to contextualize and to lead people through. In this one, I've got more maths. It's still got history and biography, but the maths is sort of driving the story. It's actually the story of the maths that is the character, if you like, the lead character. So I hope that, and so I have tried to give lots of reminders and endnotes to give more detail of people to remind them. I mean, I have assumed a basic understanding of calculus, but even there I show some detail, give some reminders of how it's calculated, what it means and how it's worked out. So in the early chapters, I do sort of try to remind readers of what they would have probably learned or wanted to learn and didn't, and as in your case with the calculus. So it's a lot on algebra and calculus. And then it starts to get into how, and of course the ancient maths as calculating and solving practical problems. Because that's so interesting in a way, because it came so practical. For example, just thinking about imaginary numbers, even negative numbers, they took a long time to be accepted. And imaginary numbers are ones where the square of the number is a negative number. And actually, that was very important to Hamilton, but we haven't got time for that now. But they were rejected as being impossible or unreal when they came up in solutions, because they didn't have any practical application. You can't have negative or imaginary dimensions of a canal or a field that they were trying to measure. So I find that that's really interesting too, just looking at that whole scope of histories, which I sort of set in, and then talk about how once I've sort of given readers a what I hope is a gentle, introduction and reminder of some basic concepts about where the search for vectors and then tenses fits in to that historical trajectory, and how you build on each part of the book is building on what went before. So I hope that there's enough there. And look, I also write so that if people decide, well, that little bit of detail, mathematical detail, I don't want to know about, or I can't, or I don't, you can skip it and go on to the
Right. And you're not going to be like so lost. I
yeah.
love that. And I can't help but feel these parallels that I often see when we talk about some of the popular science writing that does get more, let's say, more attention or more currency, like stories about CRISPR or stories about genetic engineering or all of these different topics where the story is that we had these questions and we started to want to do things and the tools did not yet exist. And so the tools had to be developed
That's
to
right.
then be used to solve the problem. And I can't help but see a parallel there when you're talking about things like imaginary numbers or even the concept of zero or the concept of negative numbers. When they don't apply and then eventually we want to ask questions and we don't have the tools to answer those questions, we got to come up with the tools.
That's right. Absolutely. Yeah.
I
And
love that. It's so
that's fascinating.
fascinating.
Yeah. Yeah.
So I'm curious about the big takeaway then. Like you've kind of told us how you hope that people will take the information in the book and how it builds upon itself. But what are some of the big hopes for people who sit down with this book? Is it really about that wonder? Is that sort of the overarching goal?
Um, yes, that's a big part of it. I mean, I would like people to feel that this extraordinary journey through the human imagination, if you like, that has led to the great theories that we have today. And not just the theories, but the technology too, because vectors and tensors are a key part of much of our technology, most of our technology, really. Because what I was saying about data before, for example, information that you can write lists, well, that means you can program search engines and things like that. Large language models that give us ChatGPT, they also use vector maths because it's about data. So I would, I guess the takeaway is this idea that this is a shared story of the human imagination. It's multicultural, it's multi-millennial, it builds on itself, but as you say, it has, you know, fits and starts, and not everything is accepted straight away. Um, but ultimately, you end up with wonderful new knowledge.
Mm, I love that so much. And it parallels one more thing with the last episode with Daisy Dunn, which is this realization that we often have, or we have to be sort of reminded sometimes that hundreds of years ago, thousands of years ago, we were the same people. You know, we might know more things now, we might have more technology now, but we're not somehow evolved into some new species. When we were Homo sapiens, we had the same capacities and
Oh,
capabilities, and all of these interesting discoveries were made by people just like us today.
yeah, solving those problems that you were saying before.
Ugh.
Yeah. What do we need to do? What tools do we need to invent? What do we want to know? And then, of course, right back in the old days, you had, in the ancient days, you had people who were fascinated with the idea of proof, for example, in mathematics, just for the sake of it, because it was just a
Yeah.
beautiful thing to do. So even thousands of years ago, people were interested in, if you like, the wonder side as well. So yes, that's a good point. That that's one of the things I want to get across. That this is a shared human journey. Um, that that is remarkable.
Ugh. Well, gosh, thank you for sharing that human journey with us. Thank you for taking the time to write this wonderful book, for taking the time to sit with us today, to teach us a thing or two, to kind of, I guess, whet our appetite about digging a little bit deeper. It's been a fascinating chat.
Oh, thanks so much, Cara. It's been lovely to talk with you.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.